Hey guys, in this video, I'm going to briefly go over SN1 and E1 reactions. And so kind of to start off, just kind of the quick rundown is with SN1 and E1 reactions, we will have the weak nucleophiles being tolerated, whereas with SN2 and E2, we know we need strong nucleophiles and strong bases. SN1, E1 doesn't care as much, and so it'll work with weak nucleophiles. And another kind of key indicator that it's an SN1 E1 is if we have a more substituted alkyl halide. And then the final thing is just kind of note is look for solvolysis and the dehydration reactions because these are both SN1 and E1 reactions respectively. So kind of just going over the reaction scheme. So we have a secondary alkyl halide in this case, and we have water. And water is not a good nucleophile or a strong base. And so it will kind of be tolerated with an E1 reaction. And so when we kind of think about SN1 and E1, we kind of think about the extremes. And so if we were to say that all of the electrons of this sigma bond right here were to go and be with that bromine, we would basically say that it kind of just pops off. And so that is due to kind of the great electronegativity of bromine and the fact that bromine is very large. And so there will kind of be like an orbital mismatch. And so the bond between that carbon and bromine is going to be not super duper strong, again, because of the electronegativity and the fact that bromine has very large orbitals. And so we kind of just have the bromine leave and we form the secondary carbocation. And then, in this case, we don't have to worry about it, but in others, we may have to do shifts or something like that. And then we have the nucleophile attack, and then maybe like a workup step, and then we kind of end with our final product. And so kind of just some notes is, SN1E1 goes through carbocation, so we need to watch out for shifts. And then the water can attack, in this case water, can attack from either the front or the back. And so we would kind of end up with a racemic mixture. There is really no preference, whereas SN2, we have that inversion of stereochemistry, and so it's very predictable what we get. But with SN1E1, we go through that planar intermediate, and so either of the kind of configurations can be formed. And another thing is SN1E1, we don't have concerted steps, or we don't have a concerted mechanism. This is a very stepwise mechanism. And so it kind of is a little bit slower, and we have a higher energy barrier to jump over because we are forming that very unstable intermediate. And then, yeah, so in this case, the water is kind of needed to, or another water is needed to work up and deprotonate the protonated water to form the final product, which is there. And so, like I mentioned before, the weak nucleophile is acceptable, and this works best on tertiary halides because when the halide leaves, it leaves a carbocation. So if we were to kind of look at all of these, once the bromine leaves, we form the carbocation, and the more kind of substituted the carbocation, the more stable. And so if we have a tertiary alkyl halide, it leaves a tertiary radical when it leaves, which is more stable than a primary radical, or I'm sorry, a tertiary carbocation, which is more stable than a primary carbocation. And so that's kind of why we prefer the more substituted alkyl halides. And then with SN1 reactions, we have what's kind of called solvolysis, which is basically where the nucleophile is the solvent. And so if you kind of see these conditions where we have the alkyl halide and we have kind of one thing, this should be screaming solvolysis because, with SN2, we have to have the nucleophile and the solvent. Whereas here, the nucleophile is the solvent. And if you see solvolysis, you know that it's SN1 or E1. Solvolysis, I think, is the SN1, and then the dehydration is E1. And then with the SN1 E1s, the rate kind of equation is this. It's the rate constant K times the concentration of the electrophile. And I think that some students may be confused why, is it just one? And then why is it the electrophile and not the nucleophile? And that's because if we think about what's happening when the alkyl halide leaves and forms the secondary or forms the carbocation, that is very, very unstable. And the nucleophile will basically attack that immediately. And so it doesn't really matter how much nucleophile there is, because any electrophile or any time the leaving group leaves, it's immediately attacked. And so the concentration of the electrophile is what's important, because if we have more electrophile, we have more potential carbocations being formed. But even if we have more of the nucleophile, that doesn't make the leaving group leave anymore, if that makes sense. And so just kind of statistically speaking, the electrophile is really only what's important, because we have that big hurdle to jump. And so if we have more kind of potential candidates to jump the hurdle, will kind of occur at a faster rate. And yeah, so there's like a long line of nucleophiles. And so if we add more nucleophile, doesn't really matter, because that's not what's slowing us down. And then, all right, so that's really all for SN1. SN1 and E1 kind of follow a very similar mechanism. And so at this point, I kind of picked up at this point right here. So what basically happens is we form the most stable carbocation, and then that's when we start branching. With SN1, we do the substitution, and E1, we do the elimination. And so what happens here, I have kind of two sets of arrows. The red set of arrows will lead to the major product, and then the purple set of arrows will lead to the minor product. Because again, this is a kind of solution of a lot of different products, and we're going to have some sort of statistic probability of forming one over the other. But with the major product, obviously it will be major, and it will have much, much more than the minor. And so what happens is the OH, or I'm sorry, the water is used to deprotonate or steal off one of the hydrogens. And the sigma electrons are basically going to be used to form the pi bond. And that's kind of because where we're at now is this carbon right here is electron deficient. But if we can use the sigma bonds as a pi bond, it will kind of spread them and make sure that both carbons are at their full octet. And so that is kind of why we do this, is that we can quench the carbocation. And so we can either basically add to it or use someone else's electrons to kind of share to make sure that it is receiving a full octet. And so that's really the only difference with E1, is that we take off the hydrogen, whereas with an SN1, we attack the carbocation. So not too bad. Again, same mechanism basically. But I did just kind of want to take a second and talk about something that confused me for a while, and that was, if we add heat, it will favor the elimination product. And so the reasoning behind that is basically because of entropy. And so if we have a substitution reaction, what we'll basically have is like we'll end up with kind of two products. And when we do the elimination, we end with more products. And because with entropy, remember that kind of the more chaotic nature of things, that favors entropy. And so if we have the Gibbs free energy equation, normally we don't really consider entropy, but with the elimination or with the dehydration reactions, I probably should do HCl as well. So with the dehydration reactions, if we increase the temperature, we basically make the entropy term more important. And so because the elimination favors the entropy, if we make entropy super important by raising the temperature, we can basically say that the heat and raising the temperature favors the elimination products. I'm not super sure if you'll have to explain why, but you probably just need to recognize that increasing the temperature will favor elimination products. If you have any questions about this, feel free to reach out. What? Good luck.